Hello, welcome to Functional Bar. My name is Charles, and in today's video, we'll be discussing user-defined types. Not all user-defined types, just a couple of ways to do that, because it turns out if I was to discuss all 4 ways we're going to talk about in one video, it's just way too long, and I think too much information all at once. So we're going to split it up to 2 very easy ones in this video. Then we'll have 2 more follow-up videos with the remaining information on how to make our own types. We'll start with why I would want to do this. We're going to talk about, like I said, 2 ways to make a new type. We're going to have some suggestions for practice, then some review, and then we'll be done. So why do we even want to make our own types, as opposed to just running with whatever primitives happen to be available to us? And this doesn't apply just to Haskell. This applies to almost all languages that have types. Not all do, but most do. Even dynamically typed languages have types, and there are ways that we use the knowledge we have to allow to kind of coerce them into using the types we want. The first reason we want to use our own types, want to make our own type, is for compile time safety. Now you've maybe heard of dynamic languages or script languages. These languages usually don't have a compilation step or anything. They might have something very similar to it, but usually it's not full-blown compilation, and so they don't get this benefit from that compilation step. It's all runtime. But Haskell is compiled. Many languages are compiled, and those compiled languages do have compile time type safety. If we use our types, if we invent types the way we need to, it makes it more and more likely that the compiler will find our bugs for us during compilation. We need the types to understand powerful to use and understand powerful features in Haskell. Now this one's mostly Haskell specific, but even in other languages, you'll have types as the basis for some of their more powerful features, especially polymorphism. Only works when you have types around, really. And object-oriented languages, they tend to call their types objects, but objects are how you introduce types into an object-oriented language. So this is mostly for Haskell, but other languages, it's really similar. In other languages, the more powerful features are based on the type systems, or at least some of the powerful features are based on that type system. And we use that type system to get us some really, really nice things. And by powerful, I mean we write a little bit of code and we get a lot out of it. The third thing is readability. That is how easy it is we can understand what's going on based on looking at the code. Types enhance readability substantially, especially in languages with type declarations, or where we, like in Haskell, we put the type above the function name. Other languages do it in different places, and having the type there really enhances readability considerably. In fact, in a dynamic language called Erlang, which is very functional in nature, they added types as or type declarations after the language was really mostly mature, fairly recently, I think. And there's a separate tool that will read those type declarations and type check your program. So it doesn't happen by default with the Erlang compiler. You use another program called Dialyzer or Dialyzer to do that. And I use both names. I'm not sure which is 100% correct. I've heard both. But the Erlang community really prefers, by and large, dynamic typing. And there's always arguments for using type declarations even without using Dialyzer, because the type declarations considerably enhance readability. So just having the type declarations there is of great benefit, even when you're not using the compiler to do the type checking for you. In Haskell, of course, the compiler buys us a lot in terms of safety, and will always let us know when we have when our types don't line up correctly or when they don't match up correctly. So in Haskell, it's very safe. We've got a lot of compile time guarantees. Finally, maintainability. This is closely related to readability and compile time type safety. Maintenance, just for those of you who may not be aware, is when we go into a program and add more features to it, or we fix bugs in it. That's generally considered maintenance. It may also be when we update the program to run in a new version of its runtime, like with Java and .NET programs, you occasionally need to bump up the .NET version or the JRE version, the runtime environment version that's going to be supported. And that it's not always 100% backwards compatibility, so there's maintenance there. Changes to the program's functionality because another system was swapped out, that sort of thing. Anytime we go into a program and change it after it's written is maintenance. Maintainability has two key components. The first is really readability. How easy is it for me to find where I need to make my change? And how easy is it for me to identify what needs to be changed in order to make it work the way I want it to now, like fix the bug or change that REST call or whatever to do something different to work with another system. So readability is a major thing. The architecture of the program comes into it as well. The other thing is the other big thing about maintainability is this compile time type safety. And that's because after you've made the change, especially bug fixes, when you make the change, it's likely that it introduces another bug or breaks something. So when you change something in a program, and a lot of software engineering is about preventing this, but if you change something in a program, it's likely something else is broken. And in the case of languages like Haskell, with strict compile time type checking, you make a change in your type, and everywhere else that type is used, automatically the compiler can tell us, hey, you need to update this. Now, if a backwards compatible change is made, the compiler can usually go through and we not have to make any other changes, but we should always expect that if we change something like a type, then we have to make changes to everything that calls that type. It may be a minor change, but we should expect to do it. There's sometimes we can get by with making a change that doesn't impact the whole rest of the program. So that's why we're making our own types. If all of this went over your head, just say it's because I don't like bugs. We use our types because we don't like bugs. So let's talk about some ways to make a new type. And in Haskell, there's really 4 major ways. We're talking about 2. And the reason in this video, the reason I've ordered it like this is because I think these are the 2 easiest to learn. And then we can use what we've learned about these programs or these ways to make types, especially Newtype. We can take the Newtype, which is very simple. It's actually constrained to be simple. It's required to be simple for reasons of performance. Newtype, we can then extend our understanding of Newtype to records in the next video, and then to sum types or enumerations in the video after that, so that we can learn all of these things. But we're just starting with these 2 because it should go pretty fast. Type synonyms especially don't require much discussion. So we're going to go ahead and get started with that. So here's, before I even start talking about adding new types, let's review the test program I've made. This should look really, really familiar. Nothing here should be new. There's some things we maybe haven't seen in a while, but everything's been covered so far. This is a function, MK for make. Remember, this is one of those the acronyms, or not acronym. This is one of the short forms, abbreviations. This is one of the abbreviations we just need to know. MK for make, so make author. Not every shop is going to be okay with that. Lots of places want you to spell it out. I'm going to use a shortened form, just MK, so that everyone gets used to it, because I see this more than make. And then if you don't know what it is, it can be very confusing. And our function is all strings. We know it's a function because it's got the arrows. So it accepts 2 strings and then returns a string. So this is a binary function, right? Its arity is 2. It takes 2 arguments, and then it returns a string. The argument names are given name and family name. And then what we do is, the parameter names. These are parameters here in the function definition. They're parameters. And then all we're doing is we're concatenating or appending the empty string onto given name and then family name onto it. So we're sticking all those strings together. We're putting given name space family name. Now, we did talk about this operator here in an earlier video. You maybe remember it better as this with the plus plus. The plus plus only works on lists, and as you'll recall, strings are lists of characters. But we're going to be using the 2 pointies, the less than, greater than operator, because this is the more general operator that works on all sorts of things that can be appended, not just lists. So we're going to use that. Also, if you're studying pure script, this is the only way you can concatenate or append strings in pure script. So our function makeAuthor takes a given name, a family name, squishes it together and as string, squishes it together and returns a string with the white space. Now there's a lot wrong with that, but before we get into what's wrong with it, let's look at the output here. This should be extremely familiar here. We've got our let clause, we've got author being assigned, and then we've put sterling show author. Now, of course, we don't have to have show author because author is a string, but I'm going to make it things other than strings here in just a minute. And I actually have an error somewhere on line 4. Forgot the equal sign. And we get what we expect. So make author, first argument, given name is Fonda, last argument is Lee. She wrote the book I happen to be reading right now, so I'm using her or her name. And then we're just going to print it, and it comes out as Fonda space Lee, as we'd expect, as a string. Now remember, because we're using show, the double quotes here let us know it's a string. Show is really good about that. By convention, we should try really hard to make sure that show looks like Haskell code that can compile into what it is. It doesn't have to. Sometimes it doesn't make sense, but we generally try very hard to make it work that way. So what's wrong with this type? The first thing that's wrong, or lack of type, what's wrong with using string for our author? The first thing that's wrong with it is we can't undo it. We can't take the string Fonda Lee and break it up into given name and family name. Now you might say, well, there's a white space there. That works a little bit until you have a first name, a given name that's got 2 words in it. And then you say, well, what about the family name? Same thing. Something like that might be a family name. And there's lots of different ways people write lots of different names. So we can't really parse them. We can, but it's very difficult to parse names based on anything. Without knowing what the names are, we have to know like the DE, all the sorts of little words here that go there. I've written a name parser. It involves a lot of data and a lot of parsing. It is not trivial by any means. So it's very difficult to parse names, especially when we don't have to. So we are, as I add the name back here, Fonda Lee back. So what we're going to do is we're going to go ahead and say that's a problem with this design. We know it's a problem. We're going to run with it and we're going to fix it later, but not in this video, not all the way. We're going to start fixing it. Another problem is these are strings. So I don't have to type names into these strings. I could type I could type gibberish. This doesn't have to mean anything. It doesn't have to be a name of any sort. And then I run it, or a name that it's unlikely this is an author name anyway. And then we just get it all squished back together like this. So we have no structure. That's the first problem, right? We can't tell what the first name and the given name, or the given name and the family name are after we've put it into an author. And then we have no correctness checking when we first create an author. It's also called correct by construction, is a big word for making sure our types line up and that we can't build something without it being correct. So those are a couple of big problems. So we're going to start up here. Another big problem, this is not so much a runtime problem, but a maintainability or readability problem. Is this just string, string, string? Our function signature doesn't tell us anything at all. We have to read the function body to know what's going on. So let's talk about the first way we can start to make some progress here. It is a type alias or type synonym. And it's just type is a keyword. We're going to make a new type called given name equals string. And that's all we have to do. This doesn't actually introduce a brand new type. it introduces an alias for a type. We'll do this for all three parts. So we've got given name, family name, and author. So now we've got these type synonyms, so we can read our make author function, and already just seeing the type declaration lets us know what's going on. It takes a given name, a family name, and it returns an author. Now I might need to know what the given name and family name are. Usually our editors help us tell that anymore, what that should be anymore. I have my own ways of finding out what that is, because I don't, Emacs will take me to the type declaration. I just don't ever do it. I just dredge about in other ways. It's just my habit. So you might want to start learning how to do that for maintenance. For this program, though, we don't need it. We just look up top and we see what it is. And there's synonyms for strings. And because it's just a synonym, we don't have to change anything else. And see, show gave us the exact same thing. This worked the exact same way, so we have no, we can just put any old string here we want. And then when we show it, it comes out as a string from show because it's just a string. Author is a synonym for string, so it's the same thing. So this gives us a lot of readability, but these type synonyms don't really get us much other than readability. And just for a refresher, strings are lists of chars, and it is fairly typical for string to be defined with the type synonym equal list of char. So that's all there is for this string. I'm going to get rid of that. So this gets us only to the readability part and helps a little bit with maintainability too, right? Because we made it more readable, but we can do better. And we're going to do better with something called a Newtype. And so this is our Newtype declaration. You see it's a bit like type, but we have extra stuff over on the right. We have the given name is twice. Now this isn't really the same thing said twice. So some of you said, don't repeat yourself. That's true. We don't want to repeat ourselves, but we're not repeating ourselves here. This is a convention. It's widely used. We don't have to, but we really should. It's like we always have to name our types with a capital letter. Like when you see all the types I've introduced here have a capital letter. This is a value constructor or data constructor or just a constructor. The type here is given name. The constructor is also given name. And because we use it in different contexts, it's perfectly fine for it to be the same. And in fact, it's recommended it be the same. There are some very good reasons for them not to be the same. And you'll occasionally run into that. But for right now, just go ahead and always name them the same thing. This is perfectly valid too. You could put foo here or whatever, right? It doesn't have to be. And it'll be clear why you can do that later when we talk about some types. But I'm going to put a tick here to illustrate something. This would compile. It's very common for Haskell programs to, when we have a name collision, like this would be a name collision, right? It's not because the compiler's smart enough to figure it out, but I want to be more clear to everyone watching that this is different. This is almost exactly, it's not quite, but very, very close to a function that accepts a string and returns a given name, right? So you can think of this as the constructor. It's a constructor function that accepts a string, and it does things, and it returns a given name. So the fact that we have the constructor function named the same as the type shouldn't really bother us at all. It's just the way we build our type. Now, this constructor here can be used for pattern matching as well, and we're going to get into that here in just a minute. There's one other thing about this Newtype declaration I want to talk about. This deriving clause. Now we're going to see a lot of this deriving clause, and I'm going to try to avoid talking about it until after we know what a type class is. But really for us to have a lot of to ease our way, we really need to know at least that it exists and that we need to type it here. So what deriving does is it says, hey, Haskell compiler, automatically make me an instance of show. Automatically make given name showable, something that I can show. So down here, when we pass in, if we were to show given name, it'd give us something. Without this, without the compiler automatically adding this for us, we wouldn't be able to put it on the console. It'd be very difficult. So we want to use the deriving show here. And we can derive several other things, but I'm not going to talk about those yet. We'll talk about those much later when we need to. So we can always follow this Newtype pattern, and just we change this to the same thing, and we can put any type here we want. It doesn't make sense for a name to be an int, so we're going to leave that as a string. And we've got family name and author as well. We're just going to add those the same way. So hopefully the repetition is helping out here. We've just done the exact same thing for each of these types. And if you follow this pattern with Newtype, you won't have any issues. You cannot have multiple things here for Newtype. Newtype, you can only have one thing here, right? You can't do this for Newtype. It has to be just one of them. So now we have our function, and our function is actually going to need to be recompiled. So I'm going to show you these error messages, because this is where you start to find that you can read these error messages. So this bottom one here, normally start with the top, but I want to focus on the bottom one because we have list of char with family name. Now, hopefully what we just talked about with type aliases, with that type keyword, this makes perfect sense to you now. The real type for a string is a list of char, and string is a type alias for list of char that we use to make our lives much, much easier, because it's much easier to think about a string than a list of chars most of the time. And says, I couldn't match type char with family name. I expected a family name. What I got was a string. That's on line 20, and it's highlighting the lead part down here. So this is the very bottom, very last error, because it's the very last thing in the file, so it's the very last thing in the compiler output. So let's go start at the top. We should generally start with the top error, because oftentimes it'll resolve later errors. Not always, but often. And so we look at this first one. It's I can't match expected type author with actual given name on line 14. And we look at line 14. It's like, what the heck is going on here? And it's because our given name is a given name, and we're trying to return something given name doing some things that it can't do. By the way, we can't append strings to given name now because this is its own type. And we're trying to return an author. So the compiler's like, I can't return an author. You gave me a given name, and the given name is doing other stuff. And so you scroll down, we'll see all sorts of other things like that. So we have to change this a bit. So this is how we unpack with pattern matching. Remember that constructor function I said, it's really important. We're going to use it again. So this is how we do it. We unpack it. And I'm going to show you how to pack it in just a minute. But this is pattern matching in the function head. So remember this part here is the function head. And we're pattern matching. So we've added our patterns here. One of the great things about our constructors and our types is we can pattern match on them. It's actually really important that we have it for Haskell. And it's being added to other non-functional languages as well. C# has added it recently, I believe. So we've got given name string, and this is given name and a parameter name. Now we know it's a parameter name because it starts with lowercase letters. We also know it's a parameter because that's the only thing that fits here. And we've done pattern matching in the head before with our lists, if you'll recall as well. This is how we do it with our user-defined types. So now this is going to work. We've unpacked it. The parameter given name is now a string value. It's a string value because of this. The same thing with family name. It's been unpacked. We've unpacked the parameter and it's given us family name. And now we see a lot of redundancy in our parameter names here. So we might want to just shorten those a bit because now it's completely possible to shorten them. It's also 100% okay to leave it as is with the longer form names. But more commonly, you'll see for such a short function, you'll see something more like this. And you can see that becomes a little more readable because it's just less stuff to take in all at once. Now, the last thing we have to do here, this unpacks a given name and family name. So we have the strings available in these parameters, but we have to return an author and we're still returning a string. So we pack up an author. Now remember, author is the same as given name and family name right now. So it's author is a string, it takes a string, and we think of that as just a function. So we have to, as our grouping symbols here, we say, hey, do all this stuff first. Smush that string together first, and then pass the result to author. And that's how we pack one of these variables. And I'm using pack and unpack because they're the functions used for some real central, it's called a text type in Haskell, and we'll talk about that later, but there are terms used in all of those libraries. So to be consistent with those, I'm using the word terms pack and unpack. Box and unbox are often words you'll hear, but I want you to be familiar with pack and unpack so that those words aren't strange to you when we get to the text libraries. All right, so now we're going to run this, and it's going to fail again. All right, now it says it could not match type char with a given name. That's right, char is not a string. This is a string. List of chars, also a string with given name. So I don't know what's going on there. Well, I know, but the compiler is saying it doesn't know what's going on. I can't do it. We've got the same thing with family name, expected a family name, but I actually got a string. So we're going to pack up these things with our constructor. This is how we instantiate these types. I use more of an object-oriented word there, instantiation and instances. We don't focus on that so much in Haskell, so if you hear me use that word, it's not the same thing as an object-oriented programming. So if you study an object-oriented language later, it's going to be really similar to the meaning in Haskell, but it's not 100% the same. We generally don't worry about instance versus class versus object at all in Haskell. It's just, this is the data, and that's that. And so now, because we have show, remember we did all that talk about the deriving show, now we can show the author. Make author returns an author and not a string, right? Because we have it up here. An author is a full-blown type. Newtype is a full-blown type. So we're going to run it. Now we have something different. We see author Fonda Lee. This is how we, the shortest way we can make author is just this. Is with the string Fonda Lee. Remember, we still can't break up our given name and family name, so make author's doing it for us. But we could write this out in our Haskell program, and it would work just fine. And I'll show you. See, now I don't need the given name and family names. I can just cause an error and not know what's happening. Hang on just a second. Oops, forgot the equal sign. This is perfectly legit. Author is just a string. We haven't learned about records or product types yet. So this is the best we can do with Newtype. So author is just a string. Next video, we'll find out how to break it up. But this is completely legitimate. We just pack it up because author is just a string. It turns Fonda Lee, the string, into an author type. So it packs it into that type. This is just saying, hey, you defined make author, but you never used it. The important part is down here. It says author Fonda Lee. That is the exact same thing we see, but it's not what we want to be doing ultimately with authors, because ultimately we want the given name and the family name to be separate. Like this. You see right now it gives us the same thing. So those are the problems we can solve with our type right now with the knowledge we have. This is not a perfect solution because we don't have enough knowledge to get there yet. I really wanted to make this one video, but it was just too long. So we're going to stop here, knowing that we haven't got the perfect version of author yet, or a great version of author. We have a version of author, and it's better than it was to begin with, where we just used a string for it. So to practice this, it is a little bit difficult to come up with ideas for just new types that are meaningful at all. So what I'd say is just make a new type for something. It could be foo, it could be bar, it could be bear, it could be cat. It doesn't matter. Just make a new type for something, and then have it be a string or an int. Have it box up a string or an int for us. And then pack it and unpack it. And remember, packing it is this thing right here. We just call the type constructor, not the type constructor, I'm sorry. We call the value constructor with the value, right, that it's going to give us. And then unpacking it, there are other ways to do it, but right now we've only really talked about this, where we unpack in the head of a function. And I'll show you real fast. We could do this, which you would never have this function, almost certainly never have this function, but you could. So I'm just going to do s because it's a string. So this would be an example of a function that just turns a given name back into a string for us if we needed that. We probably won't. It's much more common to have these as, to unpack them in the head, or in flow control we haven't studied yet called case would allow us to do that. And then our variable assignments, we could do something as well, but I'll show you real fast, but don't worry too much about this. Right. So this would give us and I think we may need, no we don't. So this would give us the variable s. So it's pattern matching, which is the assignment here. But I don't see this very often at all. Occasionally it happens in some specific instances that we haven't got to yet. But for the most part, you almost will never be using anything other than the case statement that we haven't talked about and the pattern matching in the head to unpack these. So that's it for the suggestions for practice. Just come up with something to make a new type and practice packing it and unpacking it. And you can print both ways. And then that's it for this video. We're going to review real fast. I do want to say again, this is really short. It's really short because it was just too much to lump all into one video. So we're going to have 3 shorter ones. So I'll review real fast. We talked about why we want to make our own types, how it gets us compile time, type safety. We need the types to learn more about Haskell, to learn how to use powerful features. And this isn't specific to Haskell. Other languages have real powerful features tied to their type systems as well. We talked about how it's really important for readability. It makes things much easier to read. We just look at the function signature and we can figure out kind of what the function is doing. And then for maintainability, like when we come back 6 months or 10 years from now, or we read someone else's code to enhance it, or bring it up to date or fix a bug in it. Maintainability is really important here as well. We talked about 2 ways to make a new type, new space type, the type synonyms where it says type, some name equal some type, to make an alias for that type, or type alias. It's all, both words are used. And then we talked about Newtype, which actually invents a whole new type. Versus type synonyms, which don't. They just make an alias for a type name. Newtype gives us a whole brand new type. We talked about how to pack those up and unpack those so we can use them and get our type safety. We quickly reviewed the suggestions for practice, which are admittedly skimpy for this video. They'll be much more interesting, I think, in the next video when we talk about something called a product type. And that's it for today's video. As always, questions and comments are welcome. Thank you for watching. Please click like and subscribe, and I hope you have a wonderful day.